Okay. It's a pleasure to start a second time and have a do-over. So today I'll be talking about three papers, two of which have already appeared with my advisor, Andy Sturgio, and the third, which is upcoming, should be coming out this fall, with Andy and also his other student, William Ronat. The topic will be gradient flow, and by this we mean RG monotonicity theorems. So in the mid-1980s, Zamolodchikov proved a remarkable result about two-dimensional quantum field theories, namely that the renormalization is irreversible. So there's a consistent loss of information throughout the RG flow. And the proof follows from constructing a quantity C out of the correlation functions of the stress energy tensor, which you can show monotonically decreases. And the important point is that there's a nice physical interpretation of this C in that at two-dimensional CFTs, these special points at which renormalization does not occur, there is no flow, C just becomes the central charge which appears in the CFT's Virasoro algebra. And this theorem has a nice consequence, namely that all renormalization group flows in two dimensions are very simple, and they must begin and end at a conformal field theory. And so over the last 40 years, people have tried to reproduce this result in other contexts beyond just two dimensions. There's the F-theorem in 3 dimensions, the A-theorem in 4 dimensions, and so on for quantum field theories with defects. And there have been attempts both non-perturbative and perturbative. And here I just give a sort of smattering of the works that have done on this subject over the last 40 years. And I should say that it's not just even though the motivation is very field theoretic, the goal is to study the properties of quantum field theories, the techniques that are used aren't just classical QFT techniques, there are also approaches from holography. There are attempts to tie this to properties of entropies, information theory, and finally relations to the average null energy condition more recently. And the goal of the talk today will be to discuss a particular type of monotonicity theorem in 4 minus epsilon dimensions. Is the particular context. So with that sort of foundation out of the way, I'd like to give you a basic map of where we're going to go in the course of the talk so you don't get lost. So first, I'd like to give you a picture of renormalization to carry with you throughout the talk, something that should sort of be, it's a nice intuitive understanding of why we expect RG to be monotonic in the first place, and so why we should believe that there should be theorems beyond just the C theorem, even if there aren't proofs yet. And I'll also try to introduce some other actors that will play a role over the course of the talk. Then I'd like to address this particular type of monotonicity, gradient flow, in a specific class of theories, multiscalar theories, which is wide enough to cover a broad range of examples of interesting physical theories, but is narrow enough to be tractable, as we can try to answer this question. And I'd then like to show that indeed we find that this gradient flow exists in these theories. I'd like to try to tie this to a conjecture of a monotonicity theorem, which is sort of very special because it isn't just in one particular dimension, but is instead continuous in dimensions. And it's a theorem that sort of connects all these different theorems, the C theorem, the F theorem, and the A theorem through the dimension. And finally, if I have time, in the end, I'd like to get to some other considerations, such as gradient flow and what happens if you add fermions, for instance. So this is the general plan. So first, I'd like to say sort of what I mean by renormalization. Renormalization was originally introduced in QFT as a way of curing various divergences, which appear over the course of trying to perform Feynman integrals. But it's really something physical. There's a nice picture that you can attach to it. And this is a picture that follows work by Wilson in the 70s. The idea is that you start with some QFT defined at some energy scale. So energy scale, we'll call it mu. And we want to look at what happens if we look at that theory at a lower energy scale, so mu prime. What we do is we divide the modes of the fields in our theory into 2 classes. There are high energy modes, which are called phi plus, and low energy modes, phi minus. The low energy modes, these will be the modes in the new theory that we want to look at in the low energy. And the high energy modes, these will sort of get thrown out as we go to low energy. And the idea is that we can do this throwing out by explicitly performing part of the path integral. So the partition function of our quantum field theory, which will govern all of the observables that we might want to compute, can be written in two ways. The first way is this way you'd sort of naively write it down as a theory at energy mu. You have a path integral over all of the modes in your theory, both phi minus and phi plus, with some exponential of the action in your theory. But now we want to rewrite this just in terms of low energy degrees of freedom, to get an energy, again, theory defined at a new energy mu prime. And so we'll write this instead as just a path integral over the low energy modes, phi minus, with some new effective action, which incorporates the effect of the high energy modes. And it's an important result that this effective action can basically be obtained from the original action simply by replacing the interactions that we had with new interactions of a slightly different strength. So the idea is that renormalization is a map which maps our original set of couplings, this G original energy scale mu, to some new set of couplings G prime and our new energy scale mu prime. And you can imagine that if this mu prime is infinitesimally close to mu, so we only integrate out an infinitesimal shell of our modes, then the action of this map R is encapsulated in some sort of a differential equation for G, some differential G d mu, which if you can compute what this is, then in principle you can solve for how the couplings flow at a given energy scale, and you can see how the theory changes as a function of scale.
Yeah, I mean there are drift terms which are not proportional to the couplings.
That's true. That's it. This is a sort of very heuristic, simplistic picture of what renormalization is. That's true. Those drift terms are referring to irrelevant, these extra.
I mean, they're essentially scalar theories. They imply you typically to the massive Gaussian fixed point as you flow to the infrared.
That's true. There's some amount of tuning that is required, but I mean, yeah, this picture is sort of naive. It requires some amount of tuning to get to a nice surface in your space of couplings where these which is invariant under these flows. But there is a subsurface in the space of couplings where you can describe the flows in this nice way. And what fixed points are you referring to? What is the
drift term? There's a massive term in the
but if you take the mass to zero, you get some.
But you can only take the mass to zero at one fixed point. It will be different than zero to different fixed point, and that drift will not be proportional to zero just after this. There will be a constant shifting in that. It's the naturalness problem in the Higgs sector of the standard model.
At least in the models that we consider, I think these drift terms, as long as the mass vanishes, these drift terms also vanish. That the beta function for the mass is proportional at least to the mass, and so it will vanish if you take the mass to zero, and so you do get some variant. Yes, perhaps I'm not familiar with this. Perhaps we can talk about this afterwards. But yes.
My question.
Yeah.
Like are these, to put it in a more concrete way, like high energy modes, when I think of things like quarks, and then the low energy modes, you've got the bound states of the neutron. Or,
yeah, if you like, yes. Yes, I believe that's a.
But you're only looking at scale of music.
Yes, in this context, we're only looking at scalar field theories. We're using these as sort of toy models where things are simple. At the end, I'll briefly touch on adding some Weyl fermions to this theory, but again, it's only very simple couplings are allowed, where these RG flows are under perturbative control, basically. So you can compute this beta function in sort of the normal way by removing infinities from various Feynman diagrams. This gives the beta function some expansion in terms of the couplings in your theory. And then in principle, you can try to solve this differential equation to find the QFT as a flow in the space of couplings. But in practice, this is much easier said than done. But this still, nevertheless, gives us a sort of nice picture of what renormalization is. We start at some high energy theory. We begin to integrate modes out. The couplings change, so they move on some curve through the space of couplings, and then eventually settling in some IR low energy theory. And in the very deep UV and in the very deep IR, these theories should be scale invariant and conjecture to be moreover conformally invariant. So it gives you this nice picture as quantum field theories existing on some sort of flow between two CFTs. And you can see where monotonicity comes from this picture. We've literally removed modes from our theory. We've somehow lost information. There's irreversibility because in removing this information in the IR, you can't quite tell where you've started from. You can't go back up the flow and add these modes in because there are multiple UV theories which can come from the same IR theory. But this, of course, is a bit of a naive picture because in principle, the solutions to this differential equation can be much more complicated. And this was recognized by Wilson in the early days of the renormalization group. Namely, you could have, for instance, closed curves which don't have some deep IR or UV theory at all. They just go round and round under this renormalization, so-called limit cycles. And this is where these monotonicities theorems come in. By saying that you have this monotonic quantity that's defined along the flow, you can rule out this sort of behavior. And you can say that these quantum field theories do not exist because the monotone will need to decrease, but then come back to the same position, which is a contradiction. But these theorems aren't all created equal. They come in a number of different varieties. They come in three flavors: the weak, strong, and strongest, depending on the statement that they make about this monotone. So the weakest version is the simplest. It just says that there exists a quantity which we don't define in the QFTs generally, but instead only in the CFTs, only in these fixed points of the renormalization flow, such that if any two CFTs are connected by a flow, then this quantity, which here called A, is always lower in the low energy CFT. So somehow you can interpret A as the number of states in your theory, and the number of states has decreased from the UV to the IR.
So what do you mean by this UV theory? Then you go the other way. Then you cut out all the lower energy.
Well, generally what you do is you start in a CFT and then you perturb by a relevant coupling. And so you say that your a relevant coupling being one which will increase under renormalization. So you say that the theory you started with is your UV theory, and then the relevant coupling will cause it to flow. In the picture that I sort of presented earlier with some finite cutoff, that's indeed, you wouldn't actually ever start at that UV theory. You'd start at some point along the flow and then flow down. But in principle, you can define these renormalization group flows the entire way if you start at a CFT and then perturb by a specific coupling. I mean, at least if you trust quantum field theory above to all energy scales, you can. But mathematically, you can try to define these objects.
Yeah, but you assume that any theorem, field theory, you can also do the reverse. If you take out all the low energy, and then you end up also with the scale name. Simply saying.
That's true. That's true.
Because otherwise, you would only be saying something about this particular thing, not about the general theory.
Right. The theorems apply to yes, the space of theories as a whole. It shouldn't matter which particular theory you start with. That's
UV theory should include all of the way. But then this one, by definition, UV theory assumes you take
yes.
all the way energy.
Yes.
Whereas the IR theory does not cover the high energy.
That's right.
No, you have to scalar also. Take out all the low energy. I don't think I should do. Because
No, the UV theory should include the low energy modes. It should just also include additional high energy modes, which
then you're talking about a very specific collection of field theories, not a general. How do you know that, any given even scalar field theory lies on such a trajectory?
I guess this is part of the difficulty going from beyond perturbation theory to non-perturbative theories. Perturbatively, you can, when things are under perturbative control in the scalar theories that we'll look at, you can always find the particular flow any point will be on, and then sort of trace it backwards to find this UV theory, which could be a free theory, it could be an interacting scalar theory. But you can sort of go backwards. The UV?
What is real? No couplings to force.
That's true. I guess it's a free theory plus a slight perturbation. Yeah, plus a relevant operator. That's true.
There must be some preconditions.
I mean, there are certainly some preconditions, assuming, for instance, unitarity. In the case of the C theorem, I believe it only assumes unitarity. I might be wrong. I think it's very, these theorems are generally very general. In the cases that we'll be interested in, this is within, we'll be looking at a very specific class of theories, which is a sort of the toy theories, which are very nice, have very nice renormalization properties. And so the statements that we make will only really apply to those theories. But these theories, I'd say they're still, even though it's a specific class of theories, they're still an interesting class of theories. Perhaps when I define these theories later, we can discuss that. So this is the weakest version, where you just have this quantity defined at the endpoints, but you notice it says nothing about the interior, and moreover, to get this picture, it sort of assumes that the endpoints exist. So it doesn't rule out these limit cycles whatsoever. To do that, we need to say something about the middle, about the interior. And this is where the strong version of the theorem comes in. We say that this quantity we have, A, is defined everywhere along the flow such that it monotonically decreases. And you see the strong version implies the weak version. You just take this quantity A, you evaluate it at the UV and the IR, and you'll necessarily get the weak version. But it does say something more because this extra monotonicity now eliminates these limit cycle, this possible limit cycle behavior. And in fact, we can even go further than this. The strongest version of monotonicity, where the beta function which governs this renormalization flow can be written as the gradient of another field, another scalar function, this A, and this A will be our monotone. And you can show that this implies that it's strongly monotonic, but it also gives you a bit more. It protects some of the operator dimensions in your theory. It means that they're real. So it's a sort of protection.
These is proportional to the gradient of A.
Yes.
But you can always have them. So you need some other properties. And you went through those quickly. What are those other properties?
Well, the definition of, perhaps I can, so we say that a beta function is gradient if it can be written to satisfy, if you can find a scalar function of the couplings A and some tensor G to satisfy this equation. And it is for a generic vector field beta, this isn't necessarily true, as we'll see.
So that's what mathematics.
Yes.
So you need to know your theory of physics. These are things.
Yes.
Positive definiteness is the hardest thing.
Yes. That is true.
The hardest thing to guarantee.
Yes. Yes.
So, in particular, field theories you worked on,
Yes.
how did you establish positivity?
We'll come to that later. So we construct these equations explicitly and solve them in perturbation theory to low orders. There is, I guess it's just a consequence of the particular form that the beta function has, that it'll have some particular coefficients which you can calculate, and with those coefficients you can show that you can find a positive definite metric. So I guess it's there isn't necessarily a physical principle for why, or at least it's not understood. It's in the case of, well, for positive definiteness, I should say actually there's in 4 dimensions, there's a perturbative proof of the A theorem, which takes this form where this tensor G is not symmetric, but it is positive definite. And it was proven that to all orders in perturbation theory, you can write down a scalar function A and the tensor G such that the generic, the beta function.
Yeah, I'll wait till you get there, but I mean, all orders of perturbation theory doesn't convince me of very much, because even if you've done that, unless it's an asymptotically free theory, or unless it's a well-behaved theory, the perturbation theory might be very misleading. But the thing I'd be really interested in is positive definiteness. I don't want to study that, just keep going.
Yeah, it's the proof of positive definiteness to all orders isn't by us. It was by Jack and Osborne back in the 1990s. We only do things through a certain finite loop order, and there you can just check explicitly. So this is the equation that ultimately we'll want to solve. Both properties that we demand are crucial. The positive definiteness, this is what gives the monotonicity. This is why for the strong version of the theorem, that's all you need, because this is what gives you this function A is monotonically decreasing everywhere along the flow. But the extra symmetry property is what gives you this extra thing that some operators in the theory will be guaranteed to have real dimensions. It's a sort of slight protection against unitarity breaking. And so because it's the strongest condition that you can demand of monotonicity, this is what we'll be interested in looking at in this specific class of theories called these multiscalar models. So the question I want to address today is there gradient flow both in 4 dimensions in these multiscalar theories and also in 4 minus epsilon dimensions? The 4 minus epsilon part is important because a lot of the use of these multiscalar theories is for constructing perturbative examples of 3-dimensional CFTs in the epsilon expansion. And there, because as long as epsilon is small, the RG flows are all very short, which gives some control and prevents some amount of runaway behavior. And ultimately, because we want to take epsilon to 1 in some sort of limit, we really need to keep epsilon non-zero. So we want to not just look at gradient flow in 4 dimensions, but really slightly below 4 dimensions to get some perturbative conclusions about renormalization group flows in 3 between these CFTs in 3 dimensions. I mean, we always keep it small, but I mean, in principle, there should be some limit that you can take in which these things have some well-defined epsilon to 1 limit.
Well, that's a hope.
But that's a hope. That is a hope. We always keep epsilon perturbative. But that is the hope and the sort of lore about these fixed points. And sorry.
Why do like 4 minus 1 and not like 3 plus epsilon?
Because so the particular it depends on the particular interaction term that you want. The interaction that we want has these perturbative RG flows close to 4 dimensions. There are other interactions which are perturbative close to 3 dimensions, but for the fixed points we're interested, we have to take it close to 4 dimensions to get this perturbative control. And so not to spoil things, but the upshot is that we do find that there is a solution, at least to some low loop order in 4 minus epsilon dimensions. And so we also want to try to give this a physical interpretation, a la the C theorem, where this monotone could be interpreted, at least at the CFTs, as this central charge. And also in the case of the C theorem, this metric they find, this tensor, is a 2-point function of these the relevant operators. So I want to try to give some interpretation like that. So I've been saying that we'll work only on a specific class of theories, which is very nice. This is the class of theories, is multiscalar models. The Lagrangian is a Lagrangian for n massless scalar fields interacting via this quartic potential. This quartic potential is chosen so that it's marginal in 4 dimensions and then weakly relevant in 4 minus epsilon dimensions, which is what gives perturbative control over the G flows. And here we don't really want to, so generally when people look at these fixed points, for instance, the ON CFT, they take a particular form for this interaction, some form which is invariant under ON rotations of these scalar fields. But we want to look throughout the space of theories more generally, and so we leave it to be completely general. Yes. Yeah.
Quite interesting. Written down, does that mean that it involves coefficients of the couplings which involve vector functions or something?
Yeah, they involve zeta functions and.
So does that mean that one doesn't quite know what value of those things have? What can you evaluate them on?
I mean, you can evaluate them numerically. I mean, zeta functions are defined as some sort of. They're all real. They're all.
Those are enormous calculations.
Yeah, they have various.
And it's in the epsilon expansion.
This is in the epsilon expansion. That's right. That's right.
Because the fixed dimension, 3-dimensional expansion was written down, I think, to 6 loops in the early 70s.
Yeah, that's right. This is in the epsilon expansion. I should say that for very particular values of this coupling, it's gone higher than 6 loops. But because we're keeping the coupling completely general, we can only use these results to 6 loops.
Does it become this 6-loop expression? And yet, if you would have to note how many coefficients have it?
Well, I mean, these.
Should be 0. It's in the epsilon expansion.
Yeah, these terms don't depend on epsilon. Epsilon only comes in through the classical dimension, through the first term, which is minus epsilon lambda, but this has no fixed points except for the trivial fixed point if you are in 4 dimensions. So yes. Right, the beta function, but there are no fixed points. There are no perturbative fixed points. Right. The beta function is non-zero. Is non-zero in 4 dimensions. Yeah, no. This is valid. This is valid both when epsilon is small and when epsilon is equal to 0.
It must do something simple when epsilon is 0.
The beta function doesn't simplify, I don't think.
But you see, well, then
the expansion and the coefficients with functions depending on n and special numbers.
you see,
What is that tricky?
So are you assuming anything about these coupling constants, lambda, ij,
The couplings are assumed to be real, but that's the only thing that we assume.
So there's no stability in the model at all.
No, the real and they are it's assumed to be a stable potential. We don't want to look at an unstable potential, but this is written. This is
With so many, I mean, if n is 5, I mean, it's a lot of parameters that they don't know anymore what to end up require.
is this a concern about the
You're going to show some of these expressions.
for the beta function? Yeah. Yes, I have them on the next slide. So the idea is that as I said, we're working perturbatively. We're not trying to do an all loops calculation or non-perturbative calculation. We just want to work through 6 loops to use this result, which means that this gradient flow equation will become a finite system of equations that we can solve for this function a and this tensor g. And so we expand everything in the interaction lambda, and it's easiest to represent this diagrammatically. So you can think of these sort of as just the Feynman diagrams that appear in the theory, but really they represent just structures in lambda. They represent contractions. So for instance, the first diagram in A, each vertex is a lambda, and each line represents a contracted index. So these are just two lambdas with all their indices contracted together, and so on for all the other diagrams. You can see that for the metric G, so it has two of these capital Latin indices. Each of these capital Latin indices will be the index that appears on this interaction vertex. So it'll be 4 of these little ON vector indices bundled together into a symmetrized big index. So because this tensor has 2 of these capital indices, it needs to have 8 external lines. So it's just like 4 to 4 scattering diagrams. And I'll have, again, some expansion in these diagrams. And then the beta function will have an expansion in diagrams which have 4 external legs. So the A and G, remember, these are the things that we need to solve for. So the various coefficients that appear will be the degrees of freedom that we solve for in the solution. But these B's and these E's that appear in the beta function, these are all known from the 6-loop calculation by Giombi and Pannell. I mean, there have been attempts to try to, there's a non-perturbative proof of the A theorem by Tarnopolsky and Schummer. But in this case, it's much more complicated than in 2 dimensions, when you can have these nice tools. And so that's why we're steering clear of that. We're working in this nice, simpler, comprehensive perturbation theory. Which one? This one? Yeah. Here this will be wave function. But this is a wave function normalization. We also include one particle reducible diagrams just to be complete, but the beta function coefficients are just 0. But I mean, they. It's a wave function normalization. That's right. Yeah, this is just a wave function normalization term in the beta function. That's right.
So you said that not G is a 4-point scattering angle. Is that assumed to be positive definite? G0 positive definite?
Yes, G0. Well, I mean, it's not really these aren't scattering. These aren't really scattering images. But you can think of them as the same diagrams that will appear in 4 to 4.
Yeah, I'm just worried. It's not G positive definite.
Yes. By assumption, in fact,
By assumption, it's
positive.
It's not positive.
Yes. Because we want to construct a metric that's positive definite, and we can
So you just
ensure that it's positive.
G0 is positive definite, and then prove that the effect of will change.
That's right. And that a solution still exists, and it doesn't require something.
Lines representing G.
So each line is a sort of Kronecker delta with a little.
Wait, it's just a Kronecker delta.
So yeah, I guess each line is sort of a Kronecker delta. Each vertex is a lambda, and so you can rewrite all of these diagrams in some long string of. That's right.
For example, logic of assuming Gij was a correlator of composite operators.
That's right. That's right. We'll show later on that you can interpret the solution we find in terms of a correlation function of composite operators. It's that.
That would normally involve the subtraction, so you wouldn't know what the definition.
Yes, but the metric we find is positive definite still in the end. Yes. And so now with these perturbative expansions, we can construct this equation explicitly. So remember, the equation was the derivative acting on A has to be equal to contracting this G with this beta function. So a derivative will remove one of these vertices in all of the different possible ways. The contraction you can imagine by just taking these diagrams in the beta function and attaching them to the legs on one side of the diagrams in G, and then you just simply you match terms on each side which have the same diagram. This will, because through 6 loops there's just a finite number of diagrams, this will give you a finite system of equations that you can solve for these coefficients A and these coefficients G. So to give you a sort of flavor for this, through 2 loops, everything is very simple. These are all the diagrams that appear in A through 2 loops, and you notice that they're all very symmetric in the vertices. No matter which vertex you remove from a diagram, they give you the same diagram. So on the left-hand side of this equation, dA will just look like each of these coefficients will map one-to-one to these diagrams that appear in the beta function. So you can just set the coefficients in A equal to the coefficients in the beta function with some overall numerical factor.
Where does the scale from the mu? Because you're talking about the beta function now, so you must differentiate with respect to that. Can you do that?
So the beta function will be some polynomial in the coupling. The derivative here that acts on A is just a derivative with respect to the coupling. If you want to bring in the scale mu to show that this A is in fact monotonic, the easiest way to do that is to then change derivatives with respect to mu into derivatives with respect to the coupling times the beta function. So this is where, but mu doesn't need to appear in this identification. It's this identification is true for all values of mu. It's
If the things are finite, it's true, otherwise it's.
yes. As long as the couplings are finite, that's true. But I mean, also, as if the couplings are too large, then this positive definiteness condition can sort of go away. So we restrict to some sort of small ball in coupling space.
If there's a non-empty set for things modeling, you need to play with this assumed capital zero.
Yes, that's right.
I'm not sure I understand what you're doing here. How your symbols are working. If I take the derivative of the first term with respect to
Lambda. Yeah, the derivative is with respect to lambda. Yeah.
The top term there is some function just in that bubble is just some function of n, which involves the contract, which involves contractions.
But that's those factors of n would come if you plug in a specific form for lambda, but here we're keeping lambda general. We assume all of the components are independent up to symmetry in
I
that.
mean, it looks to me like the I diagram goes like n squared, whereas you've got rid of an n squared in your vertex.
Really bottom.
This top diagram only goes like n squared if you assume that lambda has some Bowen symmetric form. In general, I mean this if you have sort of random components of your tensor, it won't necessarily go like this contractor won't necessarily go like this contractions.
Contractions, yeah.
You can think of this as lambda ijkl and another lambda ijkl.
So that's where you want to think of it. Okay, I see.
Right. We want to keep lambda ijkl general, and so just whenever a derivative just opens up, removes one of these vertices and opens up. So the two vertices, we remove one with the derivative, and that just leaves one vertex.
Okay. All right.
So it really these graphs, they're just convenient diagrammatic representations, so we don't have to write down long strings of what these lambdas are. That makes sense.
There were no non-symmetric diagrams. So these
Sure.
all seem to be very symmetric.
Yes, through two loops, you can show it by exhaustively trying to list all of the graphs that these are the only graphs you can write down. That's true, but this nice symmetry property immediately stops at three loops, where you get diagrams like this. If you remove this green vertex, you get the diagram of the beta function on the right. A blue vertex, you get this useful diagram, and the right vertex, you get this wave function normalization diagram. And so if we still wanted to just ignore the effect of this metric and just write down the beta function as the derivative of this A, we'd have to have this one coefficient in A absorb all three of these diagrams in the beta function, which you can see is a possible thing that don't work out. And this is so this problem through three loops was studied by Wallace and Zier early in the epsilon expansion in the 70s. And this is exactly what they found. They found that you need to add in these extra diagrams in the metric to add more terms on the right-hand side proportional to these unknown G's. And then that gives you enough freedom to, in fact, solve all of these equations. So the metric at three loops comes in and saves the day. But at four loops, things become even more complicated. So four loops was investigated recently by Ian, Jack, and Colin Poole in 2018, I believe. And there they found that even adding in the metric isn't necessarily enough. The beta function coefficients have to be sort of special. They have to be privileged. They have to obey some constraints. So you can't just have a generic vector field for the beta function. You have to have a very specific one. And they find that the constraints, in fact, are obeyed by the beta function that you can compute in the epsilon expansion. And so gradient flow is sort of a special, seems to be a special property.
Like your definition, like we still.
And so we go up through 6 loops, so we're 2 loop orders higher than what they looked at. And we find that the number of constraints that the beta function needs to satisfy just grows more and more. And you can see why this is the case. So the number of equations that we'll have to solve will be the number of different diagrams which can appear in the beta function. So you can think of just this as the number of diagrams which have 4 external legs. So it's some graph theory problem. You can list all these diagrams. And at 6 loops, you'll have some 819 of them. But then we'll need to solve these equations using these 2 objects, A and this tensor G. And you can see that they grow much more slowly than the number of equations.
Got some computer program to do this.
Yes, yes, there's some Mathematica. We wrote a Mathematica program to do this. Yes, we didn't solve 819 equations by hand. That would be pretty horrible. We can have a look at some of these constraints. Some of them are pretty simple and are actually easy. It's easy to understand where they come from. There's this constraint. So here the notation we use in the top left corner, this is the order in lambda. And so if you subtract 1 from this, you get the loop order of the beta function. So this is the 5 loop beta function coefficient. And this constraint just says that these 2 particular coefficients have to be equal, and in fact are equal to 36 zeta 3 squared. And to see where this constraint comes from, we have to look at the diagrams. The diagrams that they're associated with are down on the bottom with this beta function. And you see that if you complete these diagrams by adding back in a lambda at infinity, you get the same vacuum diagram. So they both come from the same A. And the important thing about these diagrams is that if you look at them long enough, you notice they have no subdivergences. So they have no subgraphs which have 4 external legs, which means that they're so-called primitive diagrams. But this means that the only thing on the right, the only thing that can absorb these diagrams in this gradient flow equation are exactly the contributions from dA. You can think of the right-hand side, the metric times the beta function, as a sort of forest structure summing over all the different subdivergences. But here, these have no subdivergences. So on the right-hand side, they'll both just be these coefficients. And on the left-hand side, they both come from the same coefficient in A. So if we to solve this equation, this one coefficient has to be equal to both of these at the same time, and so they have to be equal. And there are, of course, there are symmetry factors that are involved that happen to just cancel out. So this constraint is that they're just equal. But this is the general principle. And in fact, independently, it was known in the amplitudes community, the people who study these high loop primitive diagrams, that these constraints, that these types of constraints exist and are always satisfied to any loop order you look at. If you look at any primitive diagram and then add in a vertex at infinity and complete it and remove a different vertex to get a different diagram, the coefficients in the beta function have to be related in exactly the way such that this constraint is satisfied. So these types of constraints not only work out to 6 loops, they work out to any loop you look at, and there's a nice interpretation. But some of the constraints are much more complicated. This actually isn't too bad. There are some at 6 loops that are really quite horrible. You couldn't display on the board at all. But you see that still, if gradient flow is to be satisfied, you plug in the particular values that the company at Simpanza find, and then somehow this should be, the left side should be equal to the right side. And so you take all these constraints, you plug in these MS bar values, and you find that 5 of the 315 aren't satisfied, which seems a bit strange because, I mean, I would expect that if things don't work out, things should sort of explode. I mean, these really are horrible constraints, so why should most of them work out but not others? And in fact, the solution is that we were sort of asking the wrong question this entire time, because it's been known since this work in the 90s by Jack and Osborne that at higher loop orders, there's a sort of subtlety associated with the beta function. It turns out the beta function isn't actually invariant under wave function under field redefinitions. It's slightly non-invariant. And instead, the correct object to consider is the so-called B function. This is also what appears in the trace of the stress tensor. And this B, which is just beta plus this extra S, which sort of cancels, is sort of designed to cancel this wave function redefinition ambiguity. This B is really what governs renormalization flow, because it's the B that appears in the trace of the stress tensor. And this S, there's a very particular way, they lay it out in the paper, there's a particular way to compute this S, but the important thing is that it has two of these ON indices and it's anti-symmetric. So its contributions can only begin at 5 loops and above in these multiscalar theories, because at 4 loops and below, simply all the diagrams you try to write down are symmetric. So there simply can be no contributions. But beginning at 5 loops, there are these 4 diagrams, and you see if you sort of flip them, they don't stay the same. So it depends which side is I and which side is J.
Would never be possible to refine beta from the beginning so that it took into account general situations like this. Not better than anything, just as many as wave function. Renormalization.
You can choose a particular field redefinition such that this S vanishes, and then the B function is just equal to the beta function. The problem is that a priori you don't know what that correct field redefinition is until you sort of do a calculation. So I guess if you're very lucky or very astute, you could in fact ignore this thing entirely and just write down the correct answer from the start. But I think in general you have to be careful like this and really take this S into account.
So it's the statement that beta still use the differential flow of the coupling itself. The renormalized coupling. Whereas B must be some multiplicative factor times the coupling, the flow of that as that's an additional wave function renormalization. Is that what's going on here?
Maybe look at it this way. If you wrote down only normalization group differential equation before, and then try function in this way, say the counter answer equation.
Yeah.
That's fixed. Now, if you were to try and expand the answer correlation function in the diagrammatic form and satisfy perturbatively, would these diagrams break your solution? In other words, do you have an extra term in the Gauss and Manson equation which nobody thought was there?
I'm afraid I don't know. I believe that this B is actually what appears in the countermatic term, and that if you do the things properly, that this S just appears. This B was found this normalization group. I'm afraid the answer I don't.
I don't think we understand the definition of capital B versus beta. My understanding is that beta is the derivative of the mu of the renormalized.
Yes, that's right.
Now, B is presumably some multiplicative factor times that.
Well, how do you break?
Yes, so
Yes.
this is some other derivative from some anticipated.
Yes, I believe yes. I believe this is true, yes.
It's peculiar because leading equal to zero doesn't mean the same thing now, because you've already been talking about capital B.
So, yes, exactly. Beta is the one that must be zero. Not capital B.
You can. No, I think it is in the end B which needs to be zero for these flows. It's
The essential point, which is.
I think it's B. In order to be conformally invariant, certainly B needs to be zero because it's B that appears in the trace of the stress tensor.
Then mathematical equation, you have to have B
I believe, yes, I believe
rather than B.
so.
So lambda dot can be non-zero at that point.
Yes.
Beta can be non-zero.
Already, the lambda can be non-zero.
Yes, I believe there are, I mean, yeah, there are these flows which have, yeah, it is. Perhaps I shouldn't say more than I understand. Hmm?
Lambda is the metric tensor is important.
Yes, lambda is a symmetric tensor. That's right.
There's some kind of SOA notation.
Yes, you can think of
Capital S, some kind of SOA notation.
yeah, you can think of it existing in the Lie algebra of yes.
You're running beta into a probated.
Why would it be so notation?
Because it's antisymmetric. It's capital S is antisymmetric.
That's an infinitesimal rotation.
Yeah, it's generator rotation.
Oh, you want to be a generator rotation.
So
Yes.
can we think of capital B as being like a covariant division for beta? Is S some kind of SOA connection?
Yes, that's possible.
Certainly, if it's in the Lie algebra, I don't know if there's this. I'm afraid I don't know if there's this interpretation. I guess.
Because you could move S to the other side by taking it.
Has that kind of structure, but that's a sensible interpretation.
Looks linear.
There is a precise way to define B using the local renormalization group. I know, but beyond that, the specifics I'm not too familiar with. No, it can be found in this paper by Jack and Osborne.
The best way for finding
S can also be, yeah, there's some specific way to compute S. You make the couplings space-time dependent, and then you compute these diagrams. The space-time dependence of the couplings will introduce new divergences that require additional counterterms, and those counterterms will contribute to this S. And then at the end, you take a limit where the coefficients are space-time independent, but this S, the counterterms are still there, and that's what gives you this non-zero S. And this B. It's the idea. Okay, from the point of view of our equations, the only difference between B and beta is that some of the coefficients of these diagrams get shifted by some extra contribution from S. So you can ask these 5 constraints that weren't obeyed, are they now obeyed for some values of this S? And in fact, it is possible that they become 4 constraints on what this S can look like. Here, there are an additional 19 diagrams at 6 loops that can contribute to this S. You'll notice the first 2 of these constraints just involve the 5 loop S's, the diagrams on the previous slide. The first one, in fact, fixes the value of the second diagram to just be some particular ratio. And in fact, Jack and Osborne have now done the calculation of this S through 5 loops, and the first 2 constraints are indeed satisfied. The other 2 constraints, no one has done the calculation through 6 loops, but the fact that to get to these constraints already you needed to go through 310, which were outright satisfied, and then these additional 2, which are satisfied, I would guess that if you do this calculation, things should work out in the end.
But no, you have to check all the other constraints as well, whether they're not changed by introducing the S.
Yes, no, and yeah. Those constraints we do check. In fact, I was a bit fast. 2 of these constraints come from the 5 that aren't obeyed. The other 2 come from the other 310, which were already obeyed. Some of them are broken and become these constraints. That's true as being a bit tricky. So the upshot is that through 6 loops at least there exists this solution you can write down for this function A and this metric G, which hinges on these constraints. And the interesting thing about these constraints is that the only thing that go into them is the graph theory. You didn't need to know anything except the fact that the interaction you started with had four phi's, and then you wrote down all the possible graphs, and this is what gave you the constraint. And so it's an open question whether or not these have some nice amplitudes interpretation of the primitive diagrams, and there's some way to sort of order these constraints and then figure out from that why gradient flow seems to be satisfied. Yes.
Which is probably impossible to do, but how do you know that there's not then too many?
Too many constraints in the sense that some are not satisfied.
Because now you get constraints from the 5, then you get constraints from the 6.
Yeah.
And now about more.
I mean, you would get more constraints. You would get constraints of what S looks like at 7 loops. Presumably, when you plug in the actual values for the coefficients in S, then these would all be satisfied. That is the guess. I mean, because things appear to work out through 6 loops, it would be, I think, bizarre if things suddenly start breaking at 7 loops for no reason. At least that is the hope. At least this is sort of evidence that gradient flow should continue to hold. Okay, but as I said a while ago, we not only want to look at the solution, we want to try to find a physical solution, much like the C theorem, where this A has some interpretation, and this metric also has an interpretation in terms of some 2-point function. And I should say that even though there are constraints on the beta function, we don't use up all of the freedom that exists in A and G. So there are still some unfixed coefficients that appear. And so the question is, can we fix them in some way to give a nice interpretation for A and for G? But the problem now is that what do we match A to? So our solution was not only in 4 dimensions, but also in 4 minus epsilon dimensions. And in 4 dimensions, there's this A theorem where A becomes the A anomaly in this trace of the stress tensor. And down in 3 dimensions, there's the F theorem. But we're most interested with epsilon small but non-zero, where we have these perturbative fixed points and this perturbative RG flows that we can investigate.
You still have 3 parameters in A, G.
That's right.
3 parameters.
Through 3 loops, there are 3 parameters. Through 4 loops, there are 5, I believe. But there's some relatively small number of free parameters. That's right. And we'd like to use those somehow. But what do we match to? There's a conjecture by Giombi and Klebanov that there should exist this object F-tilde, which is analytic in dimension D, which in 3 dimensions becomes the F of the F theorem, and in 4 dimensions becomes the A of the A theorem, and so sort of interpolates. In 2 dimensions, it becomes the C of the C theorem, in fact. So it should be some interpolation that connects all of these theorems into one general monotonicity theorem. It's defined in this way. It's defined very similarly, in fact, to how F is defined as the log of the partition function on a sphere. Now it's a d-dimensional sphere. It's a 4 minus epsilon dimensional sphere. But there's this additional prefactor, this sign, which is important because in even dimensions, this log has a pole, which needs to be canceled out. They just choose this sign factor because it's simple and it cancels the pole. Such that in 4 dimensions, it turns out this becomes A, and in 2 dimensions, this becomes C.
So F-tilde is a function of epsilon mu.
Yes, but it's a function of mu only through the coupling. There's no explicit mu. There's just, it depends on the coupling, which depends on mu. That's right. And they
ZFST is the partition function of which mu?
So in this case, it's this of these multiscalar theories. But in principle, I think the conjecture is that for any renormalizable theory, if you define the partition function and then take this particular combination to find this F-tilde, that should work as a monotone, as an RG monotone. But in our case, this Z will just be the partition function for these multiscalar.
With the scale associated with SD as well.
That's right. Yes. Yeah, there's some radius. That's right.
That radius is spreading. Now appears an F-tilde. Where did it appear before? Or does it disappear from
So the scale appears generally, but it turns out that at fixed points, the scale sort of conspires to cancel. And so at fixed points, this R won't actually come into play. And so what we want to do is we want to try to sort of hammer our A to the wall by matching it with their F tilde that you can compute using this partition function at fixed points, and then use this as a definition away from fixed points. Really, this F tilde, they only define it at the CFT itself, so the scale sort of drops out of
You
F
you're
tilde.
going to relate F tilde to A
Yes,
generically.
yes,
A has no dependence on the radius of its SD.
that's right. But this so if you compute this for some values of the coupling, this will have a dependence on the radius of SD. But if you go to the fixed points, if you take the couplings to the fixed points, this dependence drops out, it cancels.
But A lives between fixed points.
Right,
And
right.
you have no dependence on A.
Right, but the conjecture is only a weak conjecture for monotonicity. They're just saying that if you evaluate it at the CFT, you get some number. If you evaluate it at another CFT, you get another number. And then in the low energy CFT, that number will always be lower. The F tilde, the conjecture isn't about anywhere on the flow in between these CFTs where this F tilde will indeed depend on the radius. So you can think of this, what this A is it's a sort of continuation. It's a continuation of the F tilde away from the fixed points in such a way that it doesn't depend on the radius anyway, if you like.
Here you were using A to the radius to U or something.
The radius, I believe, no, the radius is just chosen to be some independent parameter. But it turns out, yeah, so,
Is that only defined for like non-integer items?
yes, and that's the important point about it. This extra sign factor removes various poles that occur at even dimensions, and so it's continuous. It's continuous in dimension. Moreover, it's defined for all values of epsilon, so it should have. You should be able to track it on some epsilon goes to 1 limit. So in the end, we find that in fact you can match RA to their F tilde. So again, you take RA, you go to a fixed point, for instance, the ON fixed point or the hypercubic fixed point, and you find that after some overall rescaling by pi over 288, it is equal to the values they find for F tilde at these CFTs, as long as you choose 2 out of the 3 degrees of freedom to match. So their F tilde, they look through 3 loops, so we have 3 degrees of freedom in A through 3 loops, and we have to use 2 of them to get this matching. This extra NS shift, this is just the value of the free theory, and it doesn't depend, it's just a number. It doesn't depend on lambda at all, so we can add it to A without affecting the gradient flow equation, because when you take a derivative, it will just be killed. And so the interpretation of this is that we can consistently extend the weak theorem into a strong theorem using this A, which is defined not only at the CFTs, but away from it as well. Okay. So we also want some interpretation of the metric, and in the Zemological C theorem, this metric is interpreted as the 2-point function of these operators which govern this renormalization group flow. In our case, these operators are these 5-4 operators, are the operators that appear in the interaction. And so we want to ask, can we match the metric with this 2-point function? And so you can compute it through order lambda. These are there are 2 diagrams they compute, and then we need to add in some renormalization to renormalize these operators. But because we computed F tilde on the sphere, and we want to already sort of fix A to be F tilde, we need to work on the sphere as well when we're computing these 2-point functions. So instead of using the usual Feynman rules, now the propagator is proportional to the chordal distance on the sphere, which is some you can write in stereographic coordinates in some specific way, but okay, you can still perform this in the integrals in these diagrams and renormalize these diagrams, renormalize these operators, sorry. And in the end, the 2-point function through order epsilon will have some generic form like this, where the anomalous dimension is determined by some eigenvalue equation. Here, this, I should say, this S is a different S than it is sort of much better notation, but it's a mixing matrix for these anomalized operators. And you can compute it either using the counterterms in the previous slide or from the beta function, the one-loop beta function. Either way, in the end, from this calculation, you find that these coefficients for these quadratic operators just take these particular values, where this will be the anomalous dimension of some operator in your CFT at one loop, I should say. Okay, and we want to match this to the metric, which will also through one loop take some form like this. And we find that in the end, to do this matching, we have to rescale the operators in some way. Basically, this just comes from the fact that there's this G0 that I had multiplying the lowest term in the metric gets some order epsilon contribution. But the way we constructed the operators originally, they had were unit normalized, so we just have to normalize them differently. But the important thing is that to do this matching, we have to use our remaining degree of freedom through 3 loops. And so to match with both F tilde and with the 2-point function, we have to use all of the freedom that we have through 3 loops at least. And we guess that this means that if you wanted to do this to all loops, then you would have to really zoom in on a very particular point in the solution space. That there is one physical solution where you have this nice interpretation in terms of F tilde and the 2-point function. But at this point, the gradient flow equation takes a form that's very reminiscent of the analogical C theorem, where the derivative of this F tilde, where now F tilde of lambda is defined away from the fixed points using a solution, is equal to this 2-point function contracted with this B function.
The metric is also each other in the metric. Is that the same thing as capital I and capital K?
No, so because basically we to properly define these renormalized operators, you have to rotate your basis of operators. So this, yeah, sorry, I went a bit fast. These n's are defined to be the eigenvectors of this mixing matrix. So the renormalized operators, or alpha, are defined to be ni alpha contracted with phi I. So there's some sort of you have to rotate your basis to get operators which have a defined dimension, and the vector that determines that how you have to rotate your basis is this n.
So in general, the lambdas are run for trench sources. But the potential is not SOX.
No, that's right. That's right.
If the potential is SOX,
That's right.
it's symmetric.
Is the metric sorry?
If the potential is SON symmetric, so if you string the lambdas, so you have ON symmetric potential, is the resulting metric
Yes.
SON symmetric?
Yes. Yeah. You could just go through the diagram by diagram and do this contraction, replace lambda by the SO and symmetric lambda. And in the end, you would find everything reduces to just the first diagram, the 4 deltas, the 4 lines, times some factor that depends on n and lambda. You would get some overall.
So is the metric always ON?
No, the metric is not ON symmetric. And in general, it's not, but for yes, that's right. That's right. And in that case, if the potential is ON symmetric, these n's just sort of become delta beta j, and so it's the metric is very
Your Sij in the previous line was.
Sij wasn't the Sij that makes beta and B difference.
But it's. What is it?
It's
pulling out the scaling dimension.
this S, you can define it.
You're showing us what it's
Yes, I'm not displaying what S is. S is something like delta ij plus capital I, capital J plus some it comes from, so when you introduce some counter terms, you introduce some z factors outside the defined normalized operators phi, and then these z factors, it comes from taking a derivative of these z factors.
Also, it's a derivative of z in I times zj. Also,
Yes.
what's the t?
Alternatively, because these are the operators that govern renormalization, you can actually compute it by just taking a derivative of the beta function with respect to the coupling. So Sij is actually di beta j is another way of computing it.
I see on this.
That's right. And it has some, it's some
Yeah, no, but
delta
it
plus
makes
some
sense.
order, yeah.
Di beta j, so the interest of the generalization when the description of that. Non-solutions.
Right, that's right, that's right. Okay. But the essential point is just that we need to use this remaining degree of freedom. So we seem to get this nice, we get this solution space after we solve all these constraints, but we seem to get some nice single physical point where you get this very nice strong F-tilde theorem. Okay. So you may have noticed at the beginning that when we looked at this metric, I said that it had to obey two conditions. It had to be symmetric and positive definite. But this is also the conditions that you demand on a Riemannian metric if you're looking at some differential manifold. And so that seems to suggest that we should interpret this as a metric on the space of couplings. And so you can ask, well, what is that interpretation? What is, for instance, the Ricci scalar associated with this metric? And is it flat? And moreover, is it flat when you go to this nice physical solution in solution space? So that's, we've also examined that. The Ricci scalar will also have some perturbative expansion in the couplings lambda. It'll, as a scalar, it'll have an expansion of the exact same form that A will. So it'll be the same vacuum diagrams, but it'll now have different coefficients, which you can compute explicitly just by computing the Christoffel symbols from the metric. So you take derivatives of the metric to get the Christoffel symbols. You then combine the Christoffel symbols in the usual way, contract them up to get the Ricci scalar. And then in principle, that will give you all of these different coefficients, these R's that appear.
There's only zero R. This is at $0, which will be zero.
In the end, no, it's non-zero.
It's non-zero.
It's non-zero
$0.
as zeroth order. That's right. Which means that because this is an expansion in lambda, really this R0 is sort of the value of the Ricci scalar at the free theory, which suggests that if you interpret G as a metric, then even at the free theory spaces, the space is curved.
Just deltas. No, but that was only 1 point. You can always make them anything like that. This single point.
Right.
Okay.
That's right. That's right. So you can do this. I mean, these derivatives, they take a lot of work. Either you can put this on a computer and let it run for a couple of days, or you can do it by hand. By hand, in fact, using these diagrams is actually easier than on a computer because you can count various factors of n very easily by just counting loops, basically. But in the end, you get some pretty nasty expression for the R0 and R1, and you can then plug in the solution to get rid of most of the G's, and then zoom in on this sort of physical solution, and this is the answer you get for R0. It's importantly non-zero except for very particular values of n, but it's also, unfortunately, there is still some freedom. So this is one of the order lambda squared coefficients in the metric still appears. This wasn't fixed because we only went to order lambda when we were matching with the 2-point function of these quartic operators. So in principle, if you went higher, this one would also be fixed if you went to order lambda squared in that matching. But at this order, it appears to be unfixed. But if you look at large n, in fact, all of this sort of goes away, and at large n, the 0th order Ricci scalar is positive. So it seems to be.
Just looking at the beginning. I appreciate that, but why is it going into the Xander?
There are a lot of It's all these contractions. Basically, the lowest of each of these contractions is some factor of n. The diagram itself, it sort of just pops out. It sort of just pops out in the end if you do this counting. I don't know if there's a particular.
You can double check it.
Yeah.
But you should be limited to the connection.
Yes.
You don't have to do that. The connection could come from something else. The differential geometry, the metric in the connection can be different.
That's true. That's true.
I've seen proposals that the connection might be associated with the operator product finally. Where you see point products. You got a connection. And that's not necessarily going to.
That's true. That would be very interesting to also examine that. But in this case, we do the sort of simple thing and just take the feature connection.
Yeah, if you look at geodesic flow.
Yes, unfortunately, we weren't able to interpret what the geodesics were. They didn't appear to be privileged or normalization group flows or anything like that. It wasn't clear to us what the geodesics of this metric. But that's a very interesting question to try to figure out. So we also go to order lambda to find this 1r coefficient. Even more unfixed coefficients appear up through order lambda cubed. In the metric, you need to go higher to fix those. So we can't even determine what the sign is, even at large n. But something interesting you can still say is that because there is a single tensor structure you can construct out of lambda that has one lambda, you just take the lambda and you contract two of the indices into groups. We know that the Ricci scalar will look like some polynomial times this one tensor structure. And it's a result that for perturbative fixed points, for perturbative CFTs, this tensor structure is bounded from above by the value at the ON fixed point. So somehow this ON CFT has some extremal curvature. I mean, you can't tell if it's a maximal or minimal curvature because we don't know the sign without going to higher order in this computation, but it's still some extremal curvature, at least within the space of CFTs. In the space of QFTs, of course, as you take lambda to be infinity, the curvature blows up. But if you look at the set of CFTs, the ON CFT will have the extremal curvature. Okay, so where have we been? So through 6 loops, we can write down a solution for A and G that satisfies the gradient flow equation hinging on 350 constraints. 2 of these, we can't say whether or not they're satisfied. They would require a 6-loop computation for S, which no one has done, but 313 of them do seem to be satisfied, and some of them are quite nasty. So we believe that the remaining 2 should be satisfied. And you can give this a physical interpretation by connecting this A to this F tilde and this G to this 2-point function, at which point the metric seems to become sort of positively curved. And so it seems that there's this nice theorem of gradient flow, which curves the space of theories in some way.
But the Ricci scalar is dimensional. So what's the dimensional parameter? Is it the radius of some sphere or something? You're not talking about a dimensional subject,
But it's in field space and it's 4-dimensional.
Yeah.
So 4-dimensional, you call that the dimensionals. So are dimensionals and 4-dimensional.
so there's no physical dimensionality there. The geometry would tell you there must be something.
So the dimension of the
Well, I mean, theory space is very high dimensional. Its dimension is n plus 4 choose n. So it scales like n to the 4. The dimension of the Ricci scalar, I guess in general, would depend on n, on which particular n number of scalars you choose.
Right.
So you can ask what happens if you add fermions, and I'd like to briefly touch on that. So all we have to do is modify our original Lagrangian by adding in an extra term to include the effect of 2-component Weyl fermions. Now we have some number ns scalars and some number nf of fermions. We have 2 of these indices. We have a ONS vector index and a UNF index, which are like A and B. And this also, so in the case of multiscalar theories, these perturbative fixed points captured like the ON model, the cubic model, they're supposed to become various CFTs that you can study in 3 dimensions. Here, there are some more well-studied models. For 1 scalar, there's the Grosvenor-Yukawa model. For 2, there's the Namba-Giannolo model. For 3, there's the Karl Heisenberg model. So there are also various perturbative fixed points that are interesting in these theories. And of course, there are fixed points you find where you set y equal to 0, and then you just get back the story of the multiscalar model. So you can ask, does gradient flow still work? There's a slight complication, which is that now the gradient flow equation begins to mix orders. So if you look at this vacuum diagram, this will appear somewhere in the function a. Now we have 2 types of derivatives. We have a derivative with respect to lambda and a derivative with respect to y. If we remove the single lambda vertex, so here we have to distinguish between fermion lines, which are these bold lines, and scalar lines, which are these dashed lines. Removing this lambda vertex gives you this contribution to the 1 loop lambda beta function for lambda. But removing one of the y vertices gives you this 2 loop contribution to beta y. And you can show that more generally this is true, so that n loop diagrams in beta y should be lumped together by the gradient flow equation with n+1 loop diagrams in beta y. So if we tried to go to 6 loops again, we'd have to go to 7 loops in beta y, which it's not. The beta function for beta y is not known through 7 loops. It's only known through 4 loops, and this is very recent. Work by Thomas Steudner in about a month ago released the 4 loop beta function in this generic system. And so we'll only go up through 4 loops in beta y, which is 3 loops in beta lambda. So none of the constraints that we found before, those only begin at 4 loops in beta lambda, none of those constraints will appear. Constraints that we get in this system completely new, coming from the mixing of diagrams with lambda and diagrams with y. So you just have to turn this machine again. You just do all this machinery, write down all the diagrams, take various derivatives, contract things together, match terms, and then try to solve the equation. And in the end, we find that you can, again, write down a solution in 4 dimensions and 4 minus epsilon dimensions at the cost of obeying some constraints. So now you see there are about 1,000 constraints that we find through 3 loops in beta lambda, including about 70 constraints on this S, again, needs to appear. And now it needs to appear starting at 2 loops in beta lambda. So even though the beta function is known through 4 loops, S is only known through 3 loops in for both lambda and y. And so we can't check all of the constraints on S. We can check 4 of them. So when there are an additional 65 constraints, which we don't know whether or not they're satisfied in the end, but the rest of the constraints all work out. The ones that don't involve S, they all work out using this 4 loop computation. So again, it seems like gradient flow continues to work in the system, even if you add fermions, and so things appear to still be nice. Now you could ask, what happens if we go beyond? There, you can try to construct a generic perturbative gauge scalar fermion theory. People have looked at this not in gradient flow, but a strong version of the monotonicity theorem, and that would add just more diagrams for the complications. But in principle, you could just do this machinery again and try to get the answer. And we would guess, because you have to obey about 1,000 constraints, that things will probably work out. I think the number of constraints alone is strong evidence for the fact that there's some underlying principle at work here, which is why they're all obeyed. It'd be nice to try to understand why they're obeyed from an amplitudes perspective. So remember, for a certain class of constraints, the ones involving primitive diagrams, you could interpret them, and there is actually a proof just from the structure of the Feynman diagrams themselves that they should be obeyed to all loop orders. It would be nice to find similar interpretations for at least some of the constraints that we find to figure out why they're sort of obeyed. But that is future work. And it'd be also interesting to try to connect this. There are these various monotonicity theorems, the G theorem, the B theorem for quantum field theories with defects. And it'd be nice to try to do something similar there. And also, of course, further looking into what the interpretation is of this tensor G as a metric. There are various quantities beyond just the Ricci scalar that you can try to compute, but they just becomes more complicated. Thank you.
To do, I mean, I presume when you do the fermions as well, and the supersymmetric theory probably be easier to just scale.
That's true. You could try to yeah, you could try to, I guess, zoom in on some supersymmetric submanifold of this coupling space and then see if things are something like that. Yeah, no, that is interesting, and it's something we're trying to look at, perhaps interpreting using superfields or that sort of thing. Maybe these things simplify, but we don't at the moment. We don't know, and we also don't know. Maybe the metric has a nicer interpretation, because for in the case of in for
Maybe it's not simple.
It may not also be because maybe it's zero.
It seems a lot of the particular correction. You usually just put in something.
No, I appreciate that. Stop. Yeah. Thanks very much.
I think this antisymmetric tensor, I think that should be interpreted as an ON link. Because what it's saying is, as you, even though you don't have an ON symmetric potential, you're still choosing an ON basis. So
That's right. That's right.
You just scale and change the basis. You have to do different bases.
That's right. No, it's yeah, no, it's. I imagine that there is such an interpretation. I just don't. I don't know. I'm afraid. I can't answer that.
Lambda, when you put those indices in a lambda, you've chosen the ON basis.
Yes.
There's no reason why you should use the same basis.
And it would also make sense that you want the covariant derivative of the coupling constant to be your fixed point. That has an invariant.
If it's not covariant, it doesn't really have any meaning.
Yes, that's right.
Like you can't use capital A for S, because you've already used capital A for it.
Yeah.
Yes.
Even if that's going to just 6 loops that you go that high before you see it.
Yeah.
Yeah. That's surprising.
But I mean, this is just a consequence of the graph theory. Like it just below 5 loops, that you just can't write down an antisymmetric diagram.
Maybe what's looking for a simpler model where you could find it at lower order.
Yeah, and this is one of the advantages of working with this fermion, because there it appears already at 2 loops.
Okay. Yes.
So that's part of the benefit in this case. And also, so S is computed through 5 loops. You can ask what is its value at the fixed points that we find in like MS bar, and it turns out that for all the fixed points we know it's just 0. So in the multiscalar theories at least, so it sort of doesn't really play a role. We're not quite sure why, but for this fermion case, this S really does appear, and it's non-zero at most of the fixed points. It only depends on epsilon through the coupling lambda. So at the fixed points, the couplings will be equal to epsilon. Right.
Then you have a connection to the super. You can work with a coupling.
That's true. The dependence is only through how the couplings depend on epsilon. So I mean, it only depends on epsilon because you're looking at a sort of epsilon ball in your coupling space.
If you don't do let's say restrict epsilon.
But you could do. If you got epsilon in there, then I've got the graph, so you
could do it.
But it may not be interesting for you to do that.
What your observation is that you have a covariant derivative, which involves the derivative restricted the coupling plus an S-tilde, which that's almost orbital.
potential. If we want to, but that's only if it's a one-dimensional derivative.
No, it's an high dimension, an individual. It's a derivative in
It's
it's a with respect to the coupling of
it's a low-end connection, but the base is only one-dimensional, so it's new.
no, the derivative that was in there was the derivative with respect to a coupling. Because it was
Right.
I think I'm just thinking of beta as being a derivative, local derivative with respect to one, with respect to use. So S would be an ON connection and over mu, which is one dimensional line. Connecting one dimensional line.
I guess, yeah, but that would be the interpretation along a single RG flow. But I mean, if would I have the same interpretation if you?
If you extend it off the floor, then yeah.
Yeah.
We went fine. I want to make it base space from give you yeah. Let me be able to do it. Yeah.